Hello again, my student. I will complete the homework 6. Okay, so this question, we stopped at this question 28. Okay, in an AC generator, a coil is rotated in a magnetic field and electromotive force EMF is induced in the coil. In which position of the coil does EMF has the largest value? We said before, largest value, it must be horizontal and it will be 0 if this is vertical. So now here EMF equals 0 for the parallel to the magnetic field. We have EMF maximum. So this is why we choose A. Next. A wire connected to a resistor is moved in a magnetic field A. Okay. A current is induced in the direction shown. In which direction is the wire moved? So he gave me the induced current. Okay, and we have magnetic field from north to south. So every time he will mention to current induced, you have to use what? Fleming right hand rule. So if you use Fleming right hand rule, your first finger in the magnetic field direction and your second finger in the current direction. So now the first will be downward because the first is your thumb. So this will be downward. So this is the first finger for your right hand rule. Okay, magnetic field from N to S. Okay, and second finger toward the current. Your thumb will be what? The direction of force or motion direction. I will make it motion. I prefer motion. Okay. The diagram shows a wire between two magnetic poles. The wire is connected in a circuit with an ammeter. So now we have a current. Okay. The wire is moved downward. So this is the direction of motion. And it has a current. Okay. The wire is moved downward toward the bottom of the page. A current is induced in the wire. In which direction is the force on the wire caused by the current? Of course, if we have current induced, it will make the motion direction, or the force will be against the motion. So if the wire is moving down, so the force must be upward. So it will be towards the top again. Before we take the coil, and we said if the magnet move towards the coil will give what? Same or like pole, okay, facing the magnet to make a force, okay, against the motion of the magnet. Also, we repeat it with what? With the wire. So if the wire moving down, okay, it will induce current. This current will what? This current will produce magnetic field against motion. So the force will be against motion of wire, and due to the wire direction is to downward, so the force must be upward. Okay. This is the last question is very important. You have to know all cases. If the wire carrying a current or a coil carrying a current is moving in magnetic field, okay, so this will produce EMF, okay, and it will oppose the motion of the wire as Lenz's law, okay, said. So this is why we choose in the opposite direction motion. Okay, now diagram 1 showed an AC generator. The coil is turning as shown. Okay. So now as you see, we have a vertical position. So this position is what? Is our 0. Okay, now he said, diagram to show the output voltage produced by generator as the coil turns, which point on diagram 2 show the voltage induced when the coil is moving through the position. So because, as I said, this position is 0, so now I will choose B. This is 0. The end pole of a magnet is moved into a coil of wire connected to a galvanometer. The needle of the galvanometer moves, which situation must give a smaller galvanometer reading. We want a smaller galvanometer. It means we want a smaller EMF and current. So he said use a coil with a fewer turn and a stronger magnet. Stronger magnet will give us a stronger current. Use a coil with a fewer turns and weaker magnet. This is correct because it will reduce the current. Use a coil with more and more. So incorrect. I want to reduce EMF and the current, so I have to use a fewer turns and a weaker magnet. Okay, because we said to reduce EMF we have three options. Number one, okay, move the magnet slower. Move the magnet slower. Number two, weaker magnet or weaker magnetic field. Number three, lower number of turns. Lower number of turns. This is the three factors affect EMF induced. It will decrease the EMF induced. Okay, lower or few turns of coil. So B is correct. Now let's move to the next. A solenoid is connected in series with a sensitive ammeter. The end pole of a magnet is placed next to one end of the solenoid marked X. I think this is a repeated question. So close from the first question. Let's start with. First, the end pole of the magnet is pushed toward X, so X must be N. Then the magnet is pulled away from X. Away from X, so it must be S because it moved away, so P is correct. The two ends of a metal rod are connected by copper wire of a very sensitive ammeter. The rod is placed horizontally, okay, in the horizontal magnetic field between the N pole and the S pole of a a permanent magnet, okay, as shown in figure 9.1. Now what is the question? The rod is moved upward at constant speed in the direction shown by the arrow in figure 9.1, and EMF is induced in the rod. State two factors that determine the size of the induced EMF. We repeat it now. So we said speed of the rod, okay, and the length of the rod and the magnetic field strength. The strength of magnetic field, okay. So this is all the three factors affect the EMF. The size of the current in the ammeter depends on the size of induced EMF. State one other factor that affects the size of current, because current equal voltage over resistance. So he said one factor, V, because he said the current depends on what? Size of EMF or voltage. No, now we still have resistance. So you can write resistance. You can write length, because length depends on what? Resistance. Resistance depends on what? Length and the cross-section area and the type of material and temperature. So you can add any of this. All is correct. You have to write only one because this question has one mark only. The direction of motion of the rod is now changed. It changed the direction. It moves at a constant speed towards the end pole as shown. Now the motion toward N, it means in this direction, this figure. Okay, so now what happened? Because the wire is moving parallel, this motion is parallel to the magnetic field, so no current no EMF induced. Very important. I think I said this in the class. Okay, so state and explain what happened to the magnetic or to the induced EMF. Zero, no EMF induced. Because what? Because the wire doesn't cut the magnetic field. There is no cut to the magnetic field. Okay, so there is no field lines cut by the rod. Next, figure 9.3 show a rectangular coil of wire placed in the same horizontal magnetic field. Okay, now we have this. Now, as you see, we have the coil is parallel, so this is EMF maximum. Maximum now. Okay, he said the coil rotates in the direction shown by arrow. Okay, by the arrow in figure 9.3. An EMF is induced in the coil. On figure 9.1, sketch a graph to show how the EMF varies with the time of for 2 complete revolution of the coil. Okay, so now he starts from parallel, right? So we have the maximum. We have the maximum. So instead of this, I will change it to what? I have to start from maximum. So maximum 0, maximum negative 0, maximum this is 1, like this. Okay, now we finished 1. Next, from maximum to 0, maximum negative 0, maximum again. So this will be the second one. Okay, so we start from maximum and stop at maximum, because he said what? He placed in the same horizontal magnetic field. Okay, so I will replace this answer for this answer. This will be the most correct. Okay, of course, if you draw this one, you will gain 1 mark because you didn't start from the maximum. You have to start from maximum because the position of the coil is horizontal. It means we start from maximum EMF. Okay, and we have the first periodic time, second periodic time. 2 complete solutions. On your sketch in figure 9.4, mark a letter T to indicate a time when the coil is horizontal. The time when the coil is horizontal, this is the time when the coil is horizontal at maximum. At maximum. Okay. As the mark scheme shown, crest or trough, 1 only is enough. Yani you can put only 1 T, it's okay. Yani. Okay, now we have finished homework 6. I'm asking you, all of you, to follow this video, and you have to correct your mistakes. Okay, and be ready for the quiz soon. See you soon, inshallah. Okay.